A standard fair cubical die is to be rolled 5 times, and the number of 6s obtained is to be noted. Calculate the probability of each possible outcome, and hence deduce that the binomial distribution is linked to the binomial theorem. So we have the probability of success, which we call P, is 1/6 here. And what we should also do is define the random variable. I'll write it out this time, I won't always, but you should always. So let x be the random variable, number of 6s obtained. Now, clearly, x can take any value from 0, getting no 6s in 5 rolls, up to 5. Like so. So, let's look at the probability that x is equal to 0. Well, for that to happen, we must just have 5 failures. So that's just going to be 5/6 to the power 5. So let's go into standard and do 5 to the power 5 over 6 to the power 5. Of course, we could have just done 5/6 to the power 5. And then that is 3125 over 7776. For x to be equal to 1, we need to have 4 failures and 1 success. But the 1 success could have come anywhere amongst the different rolls. So there's 5 different positions that success could have been in. So if we multiply that by 5 choose 1, don't forget you might see that written as 5/1, that should give us the probability. So what do we have? So we've got these brackets, so we've got 5 over 6 to the power 4 multiplied by 1 over 6 and then we're going to multiply that by 5 choose 1. Well, I know that's actually 5, but let's just go and so we'll use NCR and we've got 5C1. Calculate that, and that one is also 3125 over 7776. Shouldn't have been a surprise since we know that 5C1 is 5. Now for the probability of x being 2, clearly we're going to need 3 failures and 2 successes, and our 2 successes can come anywhere amongst the 5, so we're choosing 2 of 5 places. So we've got 5/6 to the power 3, and then that 1/6 there needs to be squared, and then we have 5C2, and that's 625 over 7776. Then for the probability of x being 3, we're going to have just 2 failures, 3 successes, and of course they can be distributed anywhere. So we just need to change these powers. So this one will go to 2, This one will go to 3, and we'll change that one to a 3. And that's 125 over 3888. I'm going to write that as 250 over 7776. So they've all got the same denominator. So x is 4, so that's just going to be 5/6, this time to the power 1. And then we'll have our 1/6 to the power 4, and of course there's 5c4 places now. So reduce this power down to 1, and then increase that one to 4, and 4, so that's 25 over 7776. And finally, for x is 5, well, we know that's just going to be 1/6 to the power 5. We have to have 5 successes. And clearly the other things could have been there. 5c5 and 5/6 to the power 0 could have been there. So that's what I'll actually do on the calculator, save changing too many things. Let's go, make that one a 5. Make this one a 5. 5c5 is just 1, obviously. And there we go, that's 1 over 7776. And if we added all these up, we should get 1. And that should be clear because there are no other possible values that x could take for this particular distribution. And so therefore it's certain that we're going to get one of these values. Now, what about this bit, the binomial theorem? Well, just consider 5 over 6 plus 1 over 6 to the power 5. From what we've learnt in the past, that's going to be 5/6 to the power 5 plus 5c1, 5/6 to the 4, 1/6 to the 1, and then 5c2, 5/6 cubed, 1/6 squared, and so on. So we can see that these are actually the probabilities that we worked out here.